Hello, everyone, and welcome to Kopernik Observatory and Science Center. My name is Jeremy. I'm a science educator here. And tonight we have an exciting program on meteorology called Skywarn Training. So we'll get to that in just a moment. First, I do want to, for any newcomers this evening, want to introduce you to our website, kopernik.org. This is where you can find out all the information about our upcoming events and programs, how you can become a member. So it's here. If you go to our home page, assuming it wants to work, the home page will show you the full list of events we have going in the recent future. Oh, and there it goes. I don't know if that's our internet or if it's our website. We'll find out. But then at the bottom, too, you have our clear sky chart. And that's great, very related to tonight's talk, too. We can use that to determine our cloud cover and whether we're going to have clear skies on a given evening, especially on a Friday night when we're open to the public fully. So tonight, it's going to be a little iffy. There'll be maybe some thin clouds that we can get the brightest objects through, like Venus. We'll do our best after the program to show you something. And if not, we'll give you a complimentary pass to come back. So you can hopefully come up on a clear night and check it out. One more thing I want to talk about is our YouTube channel, which is just Kopernik Observatory, if you want to follow us there. The reason I show you this is because we are live streaming right now. There's a camera up there that I can wave to. Hello, everyone on the live stream. And we stream all of our Friday night programs as well as our observing live streams, which cover major astronomical events. So we love to have you visit on our streams too. Our chat gets really engaged and they ask a lot of questions, and it's always a lot of fun. So that's another way to interact with us virtually if you like. So you can visit us there. But I think, yeah, without further ado, we're going to get started with tonight's main presentation. Tonight we have Jake Chalupsk from the National Weather Service in Binghamton, and he's going to take you through Skywarn training. So I'll pass it off to you, Jake.
Good evening, everyone. How's everybody doing? Enjoying the lovely, lovely, lovely weather, I'm sure. We set more high records today, so that was pretty cool. I think it was 91 in Scranton, which was pretty hot for this time of year. I think the old record was like 86, so we crushed it. So this is basic Skywarn training for the spring and summer weather events. My name is Jake Chalupsk. I went to the University of Nebraska. I went from there, I moved to Houston and worked as an aviation meteorologist for 15 years, and then COVID hit and we got shut down, and happened to get lucky enough that the Weather Service was hiring at the same time and moved up here. And so it's been pretty awesome, a little different weather, but I'm not complaining. I'll take the summers here over the summers in Houston any day of the week. So this is kind of what we're going to do. We're going to do a little introduction to the Weather Service, go over the Skywarn Spotter program, and then we're going to go through some of the thunderstorm characteristics, thunderstorm hazards, the severe weather products that we issue from our office and with neighboring offices. And then we're going to go over some spotter safety. I don't know if you've noticed, but there's been we had a pretty big tornado outbreak last weekend, and it's been pretty bad, and there's been a lot of really dangerous videos being posted on the internet about trying to get the best shot and trying to get their 15 minutes of fame to get it on TikTok or whatever, and it's just way too dangerous. So we're going to go over our stuff, how to keep you safe, and then what and how to report severe weather, and then we'll finish off there. So the National Weather Service is in the Department of Commerce. Up until 1940, it was in the Department of Agriculture, and then FDR decided that weather was important for aviation, because aviation was really getting going at the time, and for national commerce, so he moved it into the Department of Commerce. And we are under NOAA, so National Oceanic and Atmospheric Administration, and there's the Weather Service. Our mission is to provide weather, water, and climate data, forecasts, warnings, and impact-based decision support services for the protection of life and property and the enhancement of the national economy. A lot of words there in one sentence, but we just added the impact-based decision support services. So that's pretty much says we work with emergency managers and other local and state governments to help when weather is around, and give them the best information they can to proceed and keep everybody safe. Now we have 121 weather forecast offices in the continental United States, 3 in Alaska, 1 in Hawaii, 1 in Guam, 1 in Puerto Rico, and there is another one in the south, which isn't on here, but there's another one in the South Pacific, in one of our islands down there. And we have 9 national centers, and the ones you're probably more familiar with are SPC, which Storm Prediction Center, which is in Norman, and then the Weather Prediction Center, which is up in the DC area. And then we forecast for about 2.5 million people, covering northeast Pennsylvania, and then all of central New York, and then Albany. Covers everything in the Hudson Valley up to a little further north than there, and Buffalo has the entire counties that cover Lake Erie and Lake Ontario. So we are located at the Binghamton Airport. Our elevation is about 1,600 feet, so it's usually several degrees warmer or cooler up there than it is down in the valley. And we are staffed 24/7, 365 by forecasters, electronic technicians that work on the radar, and a bit going for several hours. So single cell thunderstorms. So it's pretty simple with what happens with these. There's a developing stage where you get warm air at the surface. It rises up. There's no real shear to organize it, so when it rises, you get an updraft. The moist air condenses into water molecules and into raindrops, and then it falls down. Since there's no shear to do anything with this air, it just goes up and down. The cold air comes in and undercuts the thunderstorm. So now there's no more moist air that can, and warm air that can go up, so it pretty much kills itself off. And in the dissipating stage, you'll see high clouds with what looks like rain coming down, but it half the time doesn't even reach the ground. The time for this is about 45 minutes to an hour from initiation, developing stage, until dissipating stage. These still can produce severe wind gusts. It can happen if you can get a strong enough updraft to keep raindrops and small hail up in the cloud long enough. If you can get that, when that undercut happens and the updraft stops, it can all come crashing down. That happened last year. We had a small microburst of estimated about 90 miles an hour of winds that hit the ground, and it wasn't even a day that we were really expecting any severe weather. But even though they're single cell and there's not a lot of organization, they still can produce severe weather. And this is kind of what it looks like on radar. You just have this, and so I would call it little popcorn, because it's just little tiny cells, and they won't move much. They'll kind of form where they're at, go up, and then dissipate. And then their outflow will create other storms next to it, because the outflow is the lift part of the slim. That's the lift, so it'll lift up, get another part of the warmer air, give it a little boost to get that going. And so this is kind of your run-of-the-mill hot summertime afternoon thunderstorms with a high pressure overhead. This is kind of how those look in the summertime. So multi-cell, this is when we get some moderate shear going. So what this will do is the upper level winds are much stronger in this scenario, and so they'll carry the thunderstorms downwind. So they'll form the first cell, it'll move it downstream and give another cell, let it form behind it. So this organizes a little bit so that the updrafts are not being cut off by the downdrafts, and so it can kind of keep itself going a lot longer than single cells can. These tend to have a good chance of flash flooding problems, because if the upper level winds are opposite of low level winds, so this happens a lot where you get a front that kind of comes down and stalls out. Your upper level winds are going to be going west or southwest to northeast, but your low level winds ahead of that front are still coming in out of the south. And so they come up, they hit the front, they rise, and then those upper level winds carry it downstream, so you just keep getting these storms that produce cell after cell after cell and don't move. This is living in Houston, this happened 5 or 6 times where a front would come down, it would stall, and we'd get Gulf moisture coming in, southerly flow with winds out of the west. And one night we had 10 inches of rain in 7 hours. Another night we had it's like 16 inches of rain in 10 hours. Like, it happened 5 or 6 different times. And Houston floods very easily, anything over 2 inches an hour, and it is completely a mess. So so that's what multi-cell thunderstorms have a history of producing flash flooding events. So this is kind of an example of a multi-cell right here. There's your single cell, and then a multi-cell here that looks like there's kind of a boundary set up somewhere here, and we get some southerly flow, and it just kind of trains out right there and just keeps going without moving too much. Now, squall lines are driven by strong upper level winds. These new cells will redevelop along the leading edge of the storm system with rain and hail following behind. So you'll get this outflow boundary where you'll get cold air coming out of the storm running ahead of it. It pushes the warm moist air up ahead of it, and so you'll get this constant circulation of warm moist air creating the thunderstorm as it's moving. In our area it usually moves northwest to southeast, so you'll get that's one of our big thunderstorm one of our big thunderstorm makers is squall lines. We rarely get the supercell that you kind of see out in the Midwest, but squall lines are our big thunderstorm damage creators. And the updrafts and downdrafts along the line become strong, resulting in large hail and damaging winds and straight line damaging winds. So that's kind of a radar image of what that looks like. This is your heaviest rain is going to be right along the edge, leading edge of this squall line. And so all the winds here are coming out of the northwest, hitting this wind down here that is more than likely out of the south or maybe even southeast. And as soon as that cold air hits that warm air, the cold air is denser, so it goes underneath it, the warm air goes up. And so that's how you get this just continuous line of thunderstorms that don't really ever dissipate because it's kind of like an engine that just keeps itself going. That's kind of a picture of a squall line moving over New York City. That right there is a shelf cloud, and you see those when you have this cold. You see the dark back there, that's rain. So rain comes down, cold air rushes out in front of it. The warm air here over the city gets pushed up, and you get what's called a shelf cloud, and it kind of looks pretty ominous, but it's just showing you that there's going to be some strong winds coming. If you see that, you know that strong winds are going to be behind it. And then supercells, the big tornado makers. So there's a lot going on here. Supercell dynamics are pretty complicated. Pretty much it's a inflow, so you get this is the updraft here for the thunderstorm. You get a strong shear like we talked about, so it's going to be going from more than likely winds at the surface are going to be out of the southeast, winds at the mid-levels are going to be out of the south-southwest, and winds up high are going to be out of west. You have this, as the air goes from the surface up to, say 15, 20,000 feet, it's going to be doing this automatic spinning as it goes up. Well, as you stretch things, because of physics, as you start stretching that, it's going to speed up faster. So you can get updrafts as it's going up that can get up to over 100 miles an hour. And when that happens, you really get a lot of you can get very strong tornadoes. Just because we have a supercell doesn't mean that there's going to be a tornado. Only around 20% of supercells produce tornadoes. But with those strong updrafts, you're going to get large hail that gets stuck up here and gets elevated in the cold, below freezing part of the cloud. So you're going to get hail that's above ping pong ball size, gets up to baseball, softball size hail out in the Midwest. Not as much here. Here we just don't have the dry air from the Rockies or Canada, and don't have as much moisture like they do from the Gulf. So we tend to get golf ball size, maybe sometimes. I can't remember what the record is for around here, but I know that there's been some baseball-sized ones before. So back to the supercell. So you get this forward flank downdraft. This is where all the rain and hail is. So you get that cold air coming down. It pushes out this gust front, so you can get cold outflow here. This is where you're going to get damaging straight line winds. This back, what's called a rear flank downdraft. So all the air at the mid-levels is going to hit this storm and kind of get caught and pushed down. So when it does that, it hits the ground, and it causes a gust front in the rear of it. Now when that air hits the ground and comes out, it can get wrapped up with the inflow from the surface with the more moist air, and that's where you're going to get your tornado genesis, when you kind of get all that twisting of the air going on when it hits this strong updraft. Like I said, when you stretch it, it really speeds up, and that's where you get your tornadoes. So this is a picture of a classic supercell. There's a diagram up here that kind of shows you what's going on here. So here's your inflow right here. So this is the winds coming out of the south-southeast. Here's your rear flank downdraft back here. It hits the storm here and it goes down, so there's your rear flank. This is your tornado with more than likely debris showing up on the radar. This will be hail right here, and then heavy rain, and your strong winds are going to be coming out this way. Let's see. Yeah. So if you're looking at it from the ground, that's kind of what you're going to see. The real strong storms, you know it's a strong storm if you see what's called an overshooting top. That means the updraft is so strong that it's able to push water vapor up into the into the tropopause. Because once you hit the tropopause, it starts to warm as you go up. So usually that's the boundary. But if your updraft is strong enough, the momentum that it takes will break through that. So an overshooting top really gives you a good idea that the storm that you have and you're watching is pretty strong. And then from here, you're going to see, sometimes it'll be hard to tell the difference between cloud and ground with the rain there, because they're going to be the same color. And then your rear flanking downdraft on the backside, it's going to look like tiny little thunderstorms trying to build up. And then your wall cloud is a part of the updraft that descends down lower to the ground, and your tornado. And that's just another picture of my mountainous clouds. It just shows the air hitting it and then kind of rippling as it bounces along the tropopause. And here's your main updraft in here. Okay, so this is a kind of shelf cloud I talked about earlier. It's from a squall line moving over Lake Ontario. So you can kind of see what it looks like. So here's the cold air pushing all this warm air up as it's approaching. And then you're going to see what looks like pollen maybe get blown out of these trees as it comes. And then I'll play it again. It's only 15 seconds. But behind it, you can see the water. You can see the water just kind of getting pushed from far to near as after that goes. It just shows you again how strong the winds were. Yeah. Yeah, that's not what you're going to see while you're looking at it. It's going to go. Yeah, that's going to rip a bunch of stuff up. No, that's a time lapse. You're not going to see it. You sit there and stare at it long enough, you'll be able to see that stuff going. But yeah, it's going to be. It won't look like that. So thunderstorm hazards. So let's get into what thunderstorms produce. So for a thunderstorm to be severe, and needs to have hail that is 1 inch or larger in diameter, needs to have winds of 58 miles an hour or greater, or an active tornado. It does not need lightning. That's present in every thunderstorm, and flooding is not necessary for severe thunderstorm. That's a whole different category. The 58 mile an hour number is from studies were done a bunch of engineering study. People worked with weather people and did studies on what wind speed really started causing a lot of structural damage, and they found that 58 miles an hour and above is where it really started causing damage like this on that grain silo. Anything below that, the damage was exponentially smaller. So that's where that number comes from. It's not like they just didn't pick it out of the air and say, oh, 58 sounds good. So straight line winds, these are most associated with squall lines, like we talked about earlier. The forward movement of the storm combined with the transport of strong winds aloft down to the surface. And they develop a bow echo on radar, which is a good indicator of where the strongest winds are. So if you're looking at a radar and you kind of see this bulge on a squall line with what looks like clearing behind it, that is a very strong indicator of very powerful winds. Because what this right here is, this is air descending from mid-levels. So you're going to have what's called the mid-level jet, where it's running at sometimes 70, 80 miles an hour. And if it gets dry air gets pushed into it, it can get caught up and brought down to the lower levels of the atmosphere. So when it descends, it dries out, and so that's why there's no radar reflectivity. It's real light here, so that's a good indicator that you have a rear flank inflow coming in that's going to be very strong winds that's pushing this bulge out. So this is reflectivity when you look at it on, and I don't have a picture of it, but when you look at it on the velocities on the radar, you're going to see a very concentrated area of strong winds right here. Straight line winds from squall lines are a big damage creator here in our area. So this is one of the things we are always looking for. We call them QLCS. It's a quasi-station storms, and they're a very big pain in the butt, and they're not easy to forecast for. But stuff like this we can really use to help get our warnings out pretty quickly. Yes. Yeah, we'll go over those here. That's actually next. So when we're looking for damage, the direction is going to be all in the same. It's going to be all in the same direction. It's not going to be any crisscrossing. All the trees are going to fall down the same way. That's a straight line wind fingerprint, because the winds are all coming in one direction. A tornado would be twisting, so stuff would be falling over each other. So if we're looking for, when we go out and do a damage survey, we're looking at the damage pattern to see if the trees have fallen down in the same direction. So downbursts are also straight line winds, just a different form of it. So downdrafts develop when raindrops grow too big to be suspended in the air, and then drier air gets ingested into the storm, leading to evaporation. So the drier air is more dense and colder than the moist air, and so it will it'll pretty much cause it to rapidly fall to the ground. And these downdrafts are usually, if you call them a microburst, it's going to be less than about 2.5 miles. Or a macro burst, which is less common. It's going to be more than 2.5 miles. I got a video here that kind of shows what it looks like. So that just all that rain, that updraft failed, and all that rain just fell out of that thunderstorm at one time. And you can see right here, it hits the ground and just boom. And it even kind of hits and curls up. That's how fast it was going down. And these can regularly be 90 to 110 miles an hour. And people will, it just obliterates whatever is in that small area. Yeah, it's not, the time lapse is very fast. It's not like that other one was 45. It started at 1847 and it's now, so yeah, it's very fast. Yes, that is correct. So downburst wind damage, because it's all coming down from one area and kind of spreading out, it can sometimes look like tornado damage because it's not all going in the straight line, because it'll hit at one point and then kind of spread out. So it could look like tornado damage, but it's more spread out instead of crisscrossing over itself. So let's start talking a little bit about tornadoes. We're going to go over some terms to kind of get you guys some clarifying terms on different parts of tornadoes. So a wall cloud is the lowering of clouds around an updraft of a thunderstorm. This will have broad rotation, and that's a good sign that conditions are ripe for producing a tornado. Wall clouds are ominous looking, but they don't cause damage. They just spin. They look like spaceships, pretty much, and they're really cool as long as they're not producing a tornado, because then it gets bad. But and so a funnel cloud will be a narrow rotating funnel that extends from the base of a thunderstorm inside that wall cloud. It doesn't reach the ground. Not all funnel clouds turn into tornadoes, but again, if you see one, it's a good indicator that storm could produce one, so make sure that you're safe and in a good, safe location. And if it is observed, like I just said, assume it will generate a tornado and get to safety. And then tornado, the violently rotating column of air extending from the thunderstorm and actually gets in contact with the ground. And we estimate its strength based on the enhanced Fujita scale, and that's pretty much on how much damage the storm causes. So tornado structure, it's a little confusing. So they're very complicated, and just recently we've really started to understand the structure of them a little bit better. So here's your wall cloud, and this is just kind of a blown up image of it. So from your wall cloud, you've got this surface inflow layer. Here's your rear flank downdraft. It gets sucked up by the updraft, stretched so it's spinning fast, and it's got this inner structure of where there's air that kind of flows down the center of the funnel and then hits the ground, and with the outside updraft gets sucked back up. Now it's hard to see, you really can't see all of this a lot because of the dust and debris that goes around it, plus the condensation funnel that covers it as well. So getting to actually see the inside of it is very rare, just because of all the stuff that usually is around the storm. So here is our enhanced Fujita damage indicator. So it goes from EF0 to EF5. Us in the Northeast, mostly it's EF0 to EF1. Every now and then we'll get an EF2. EF3 is very, very rare. So EF0 is going to be minor damage. You know, you're going to have shingles blown off, some trees snapped, nothing too different than what straight line winds would cause. An EF1 is got 86 to 110 miles an hour. This is more moderate. You're going to have significant roof damage, doors and windows blown off, mobile homes overturned. And then EF2, you're getting up into the strong tornadoes with considerable damage. You're going to have whole roofs torn off. You're going to have well-constructed homes kind of knocked off their foundations. And then trees are going to be snapped or uprooted, and cars can be moved easily. EF3, pretty much entire second stories will be destroyed. Damage to very large buildings, homes that aren't secured properly to their foundations will get completely blown away. Trees will start to lose their bark, or all their limbs will start getting pulled off. And then EF4, which the last outbreak that we had several EF4 rated tornadoes, which go up to 200 miles an hour, and well-constructed homes are leveled, cars are thrown significant distances, top story and exterior walls of masonry buildings are likely to collapse. You can see that here, and you see this car chucked into this tree here. And EF5, which is incredibly rare, and we haven't had one in a very long time, but it's pretty much, you know, if you ever watched the movie Twister, it's the finger of God just going through and wiping absolutely everything out of its path. It'll rip up concrete off the ground. It will completely throw homes off of concrete slabs and take the debris with it, so it looks like there was nothing even there to begin with. If you ever get, hopefully no one ever has to experience that, but if you were ever in an EF5 without being underground, in a very, very well constructed storm shelter, you would probably not survive it. So I went through, we redid our presentation here this past spring because our old one was kind of out of date. So I found a video. This is a tornado from Andover, Kansas. And this thing is super cool because it formed along a dry line. So the air at the surface is super dry. So it doesn't create the condensation cloud. And you can really see what goes on inside the funnel. And so this guy's taken, and it's muted because he's cursing a lot. But right now he should know he's in trouble because everything is getting ripped off. He should have been gone a long time ago. This was an EF3. They measured about 155 miles an hour, they estimated. So it goes up next to a school, and the school security cameras are able to capture it. And so it...
Now those flashes are lightning happening inside?
No, that was transformers.
Oh. All that popping into other...
Yeah, those were transformers. And so this is very narrow. It's not very wide at all, but you can just see that it doesn't take much.
Security camera installer.
Yeah, exactly. The flags are holding on for dear life too. That person that owns that car has got to be pretty excited. Looks like a Tahoe. It didn't budge at all.
Imagine having your dash cam footage. You just see a tornado go right by your car and it doesn't move.
Yeah. Let's see here. Yeah, it is. Here we go. There's just a lot of security cameras from the school. This is the parking lot, and it goes right by, right through the parking lot here. And there it is. Yep. And there goes the car. Security camera's still working, so that's good.
I struggled a little bit, but with that space, I don't blame it.
And then let's see here.
Stay on this one for a second, if you don't mind.
This doesn't do anything. So this is why you do not, if you're in school and a tornado warning comes, you get inside the hallways with no windows, the center part of the school, because this is the cafeteria, and everything just kind of gets sucked out as...
The garbage can is like, nope, I'm out.
Yeah. So always, if you're in school, get out, away from the outside walls. Let's see here. That's not good. And then this one, you can I can't remember at which part of the storm this is, but you can see the wall cloud up here slowly rotating, and then it just speeding up as it gets closer to the ground. But at this point, I think it hit a bunch of dirt, so it was able to show the entire funnel. Because for a large portion of this, every now and then the funnel would descend, but it wouldn't touch what was going on at the surface because the air was so dry. It's just very, very rare what this storm was able to do, and it's how you could see just what was going on inside. Okay.
At the beginning of the video, there was it looked like that funnel part kind of like that, but there was also air moving around. Was that where the condensation curtain would be? Yeah, you can see the inner part and there's kind of...
Yeah, a little bit. It usually is shrouded completely, but it's also sucking up all this dirt and everything that it's blowing through.
Those things can also have multiple vortices.
Yeah, the bigger ones that have, the ones that they say that are 2-3 miles wide, they will tend to be one giant mesocyclone, that one giant big rotating column of air that pretty much descends down, and then within it you'll get 3 or 4 of those. And so I got also another same storm, but it's from a drone, and it is pretty cool. So it's going right through a residential area, and as you can see, there's no, it's all debris. There's no condensation cloud or anything really, and you can just see it ripping these houses to shreds as it goes through. Nope, this is real time. No, there was a warning out. Yeah, you'd see it on the radar, and they had, and that's kind of cool. The vortice kind of falls apart as it crosses this from the field into the housing development. And you can see it it's really, really spinning super fast right here. And then you go kind of up here, and it's spinning fast, but not nearly as fast. But you just see the tight, very tight rotation down here that gets those winds going like that. Yep, exactly. Yep, centrifugal force. If you make your radius small, you'll go faster. That's that stretching I was talking about. So it's the same drone video, but he just kind of zoomed in on where he was at, because if he was any closer, his thing would have gotten tossed. Because I think he followed it for a while. So it's kind of, this is another angle. So you can see the funnel cloud portion of it kind of comes down, and then it goes back up. As it's not really connected, but it definitely is connected by condensation, but it definitely is connected from the thunderstorm down to the surface. And then all this debris flying around, and most of the time, tornado doesn't kill people, it's the debris. Because the boards and anything flying around it, 75, 100 miles an hour, if it hits you, you're dead. There's just no surviving that. No, too strong. You're talking about tons of water and winds that are just too strong for man to pretty much do anything about.
Right, it's like, I remember my force calculation for it, it's the pounds times the miles per hour, so that chunk of wood is only, 5 pounds times 700 mile an hour wind is
Yeah, it's flying through
having a natural hit to the stomach.
pretty crazy. Okay. So this is kind of what we get up here. And this is a tornado, an EF1 up in New Hampshire. And there it is, right there. Now this, I'm assuming, is a spotter, maybe. I don't know exactly who it is. So, yeah, so he pulls off here, and which he should have turned around and left, but because it is coming right at him. So he just kind of waits, and he gets lucky because it kind of it weakens a tiny bit as it's getting closer. It's not as wrapped up as it was. Well, this guy is not paying attention and just yeah.
Did you see when the pickup truck was picked up and dropped and the guy drove away?
Yeah. Yeah, Chevy gave him a new truck after that. So
I got a new truck out of it.
So that truck got lucky because that tornado kind of dissipated as it got here, and this chaser got lucky as well. And then you can kind of see the damage as it went along this road of all the trees that it snapped at the base. So this is more what our tornadoes are like. We don't get the classic supercell, humongous F3, F4s that the Southwest and the Midwest get. We just don't have the right dynamics. It's not saying that we couldn't, but just for our normal weather patterns, we just don't get that type of.
Back in 83, Chemung County had an F3.
Yes.
And I was in central Pennsylvania in 85 that had the tornado outbreak in Pennsylvania. Which were F3s, F4s.
Yeah, and that was back before they changed the Fujita scale, so in EF now. So a lot of the storms that they rated higher back then would be rated lower now, because they didn't know as much about the damage indicators. When they go and look at the houses that get knocked over by these storms, they understand that if it's built a certain way to a certain spec, they know that a certain wind speed will have to be reached to destroy it that way. So they go in and half of it, I mean, the warning coordination meteorologists that go through and do that, I mean, they have to be almost engineers in looking at this stuff and seeing, you know, was this hammered incorrectly? Was this screwed incorrectly? To figure out exactly what wind speed would take to knock some of this stuff out. And that gets real tricky when it starts getting up in the higher EF ratings, because they have to start getting real particular with it. And so yeah, it's pretty much just a traffic jam now.
So I know no vehicle is really safe, but are lower to the ground vehicles safer?
No.
As well?
Nope, doesn't matter. Tornado doesn't care. It'll lift you up either way. So here's what tornado damage would look like. It's hard to see, but the trees here are crossing this way. Trees here are crossing this way through what is the center vortex of the tornado. You can also see ground scarring here. So it's pretty much just lifted all the loose topsoil up and gotten down underneath to more packed soil. But the winds are spinning this way, so it's spinning here, and then over here they're spinning there, so that's why it kind of converges on the center of the funnel. So on radar, this is kind of what it looks like. Here's your reflectivity, where there would be your tornado right there. Here's your inflow, and here's the velocities. So we're looking at a radar that is up here. So here's your outbound signatures there, your inbound here. So you're getting this spin right here of this very small area. So that's what we're looking for when we're looking for tornadoes. We're looking for what we call a couplet, a very small couplet. So you're getting one box right next to each other of air that's going super fast one way and super fast the other way. Inside this larger, what we call a mesocyclone. So this would be air moving away and then air coming in, and then you're going to get tighter, much faster spinning within that. So spectrum width here, that pretty much just tells you what things are doing inside, or what things are doing. So if these reds here, it means that it's being jostled around a lot. It's not uniformly moving. It's got a lot of chaos in it. And the correlation coefficient lets you see the uniformity of the objects that are within the radar beam. So this red stuff means that everything within the beam that is being sampled by the radar is kind of the same size. When you start getting to these lighter colors, and especially this blue, it means that it's sampling different sizes that are much different than what is over here. So this is going to be either inflow, because it'll pick up bugs and stuff, and when it sees bugs, bugs don't look like rain, so it will start showing up these different colors. And so this is because this storm is here. See this little blue right there? That's probably debris matched up with that dark color. It's the sizes of the particles that the beam is measuring. So if it's looking for uniformity within the beam, so anytime that it samples something in the beam that is much larger than what of the other things that are in the beam, then it starts spitting out these different numbers. So the reds are like, it's out of a scale of 1, so the reds are like, here you can see it on the side, the reds are 100 to 95, and then this area is when you start seeing hail, and then anything below 80 to 75 is going to be like super large hail or debris. And when you start getting the blue, it's either debris from a tornado, or it's bugs or grass or something that's getting picked up by the radar. So a QLCS, like I said before, quasi-linear convective system. That's another name for a squall line, but that's what we get here. And this is the most type of tornado in our county warning area, our CWA. Problem with these is they are very fast. They will spin up and spin down within one radar scan, which is about 5 minutes. So we miss a lot of them, and it's unfortunate. I missed one last summer that came from Buffalo. They weren't warning it. It came right into our area, hit a town, picked itself up and kept going, and it didn't even show up on the radar scan. It was so fast because the EM out there called us and said, "Oh, we got a lot of damage." And I was like, "What are you talking about? There's nothing going on." And sure enough, yeah, it was a tornado. It was about 50 yards wide, on the ground for 150 meters. Yeah, it'll be these little nubs, to where you see you're going to have all this this red here is going away from the radar, so the air is going away, and you'll get these perturbations within that line that allows this inflow to kind of spin, and it's hard to predict, and there's lots of things you're supposed to look at, but sometimes it takes longer to look at what you're supposed to be checking on the radar before it's already started and finished. So you have to really be on your game and have a lot of people watching radar at the same time to catch a lot of these ones. Yeah, those are a combination of that and supercells. Because you can have supercells within a hurricane, but I am not an expert on hurricanes, so I could not tell you exactly if it's those same types. But yeah, because while I was in Texas and Houston during Hurricane Harvey, we had 16 tornado warnings that went over our house. Nothing ever hit the ground, but it was spinning in the atmosphere, so they had to issue it because we had a couple that hit the ground, so they just assumed that all the other ones were going to hit the ground. So that was not fun at all. So hail, the other, besides wind, what else we can use to classify a thunderstorm as severe? So with hail, you need very moist air at the surface. It gets pulled up into an updraft and gets above freezing. And then it's got to stay above freezing. And it's the updraft has got to keep it going. So the updraft has to be strong enough to allow these hailstones to grow. If it's a weak updraft, it'll go up, create some small pea-sized hail, and then they'll fall at the backside. And by the time it gets below the freezing line and starts warming up, it's already melted and it hits the ground as rain. So you really have to have a strong enough updraft to keep it up, and you need some shear in the upper levels to move this hail outside of the rain shaft. Because they did a study about a decade ago that the greatest thing that caused hail to melt as it was falling down wasn't ambient temperature within the thunderstorm or how high the freezing level was. It was whether the hailstone fell within rain or not. So if it falls within the rain shaft, it's going to melt. It was a factor of 10, how fast it melted, versus if it just fell outside the rain shaft, the freezing level didn't really matter. The size of hail stones that they had after 8 minutes between, it's one was simulating the ground being 85 and one was simulating the ground being 75. It was negligible, but if it fell within rain, it melted much faster. So to get real severe size hail, which is what we're looking for, is quarter over here on the right hand side and above, you need an updraft speed of about 50 miles an hour. And if you have some stronger shear within the storm at the mid levels, you might be able to get a little bit lower. But for a normal storm, you need it to be at least 50 miles an hour. And then down to get softball size, you need at least 100. And that's including the strong shear to separate it. What do you mean? Oh, it can get bigger. That's just we use for hailstone size. We like to use everyday objects, so people pick it up and they kind of see it like, oh yeah, that's. I mean, it gets kind of a little crazy with walnut and golf ball and hen egg and all these ones in here. It's like, okay, well. I can't remember what the size of the biggest. Something around 8 inches. Yeah, it fell in Nebraska or Kansas or somewhere, and it was almost 8 inches, I believe, but don't quote me on that. So that's kind of how we need hail to form. We need a stronger enough updraft to keep the stones aloft, and we need enough shear to keep the stones away from the rain and let them fall. Now, if you're ever stuck outside and you start seeing a plop of hail, 9 times out of 10 it's slow. You'll see one stone and then the other, and it's like, what is going on? Like what? Like what? And then all of a sudden you realize, oh shoot, this is hail. I need to run, because it's usually like 1, 2, 3, 4, 5, 6, and then it just all comes at once. But at least, more often than not, you get a little bit of warning, because it doesn't immediately. It's not like rain where it can just automatically just start coming down like cats and dogs. So this is kind of how you see hail on radar. So this is what we call a 3-body scatter spike. So what this is the radar is pointing up here. It's scanning down. The radar beam is hitting this hail, getting deflected to the ground. Then it is bouncing back to hitting the hail again, and then back to the radar. So it picks that up, and the radar doesn't know that it's hitting hail, so it thinks that those return beams, it's picking up way out here. So whenever we see these long, extended radar returns, we know that it's hitting pretty big hailstones within the thunderstorm, because the radar beam comes in, hits it, bounces down, up and out, and so it reads it as, it doesn't know that it's bouncing and hitting the ground and coming back. So it measures it by time. It hits the pulse and it listens, and whenever that pulse comes back, that's how it does its distance measurement. And so when it takes longer than it thinks it should, it says, you got stuff out here, when really it's just hitting hailstones.
The little defaults get detecting on that previous one, there's a bunch of little.
Yeah, probably. Probably, yeah. So this is a kind of a side view of what I was just talking about. Where here's the thunderstorm core, the updraft here. The radar is coming from this way, so it's hitting this stuff. It's bouncing to the ground, bouncing up, going back, and then the radar thinks, because it's doing this extra stuff over here, that it's getting returns back here where it's not. So the radar, even though it is super advanced and very technical, it creates a lot of errors. So you have to understand what the errors are when you're looking at a radar return, because there's a lot of things that it will spit out that look awesome that maybe you should warn on, but it's really just an error because it's picking up something high in the atmosphere, even though it's showing, say it's showing a tornado velocity signature here, because it's doing what we call side lobing, where it's picking up strong winds above it, but because it's being reflected differently, it's showing it down. So we got to make sure that where those velocity returns are coming back, that there's actually a DBZ signature where there's actually showing something going on. And a lot of times there'll be strong winds on the velocities, but there'll be nothing actually there in the radar. So this is kind of what it looks like, what we're looking at with our tools here. So usually when it starts getting above 60 dBz, we know that's starting to pick up ice and hailstones. This ZDR is a measurement of spin. So radars shoot a beam this way and shoot a beam this way. And that's why it's called dual polarization, because it's going one way and then the other. And when it does that, it can tell if what it's measuring, if it's flatter or if it's narrower. So when it comes back, it'll show a bunch of flat things. So because when raindrops fall, they fall and they have wind resistance against them, so they kind of flatten out. And so it'll send back a reading in rain that shows it's whatever the numbers correlated to it. That's what we know is rain, because it's the return that it's getting is kind of flat. Well, if it's coming back with a lot of things that are narrow, it's the other side of the spectrum. So when we start getting returns that are near zero, it's showing things that are spinning and spherical. And so the only thing that would be spherical within a storm would be hail. All the water droplets are going to be flat like pancakes. And so anything that comes back near zero, we know is going to be a hail signature, and then you can correlate that to what you're seeing with the returns. And then down here, the KDP, which these higher numbers are showing high water content, much higher than what a normal raindrop would be, because that is water melting on the outside of a hailstone. So it thinks it's this huge raindrop, but it's really just a big hailstone that's covered in water. So you'll see these numbers here that show these higher returns correlated to where the high DBZs are, correlated to where the ZDR is. And then the correlation coefficient, where you're looking at the ratio of what the radar is scanning, if it's all similar or if they're different sizes. And so when you start getting yellows and blues, those mean that whatever's in there is a different size compared to the other things that it's sampling in its scan. So when you put them all together, it's a pretty good indication that you've got hail, and we would issue a severe thunderstorm warning for, in this case, with that high of a DBZ, it'd probably be golf ball, and that's what they got in Huntsville about a decade ago. So large hail, it's definitely not circular. It can be, depending on just that type of storm, but you can kind of get these elongated shapes. It just depends on how the hailstone grows within it. It might get a bunch of stones mashed together when they're very still wet and forming, and then they'll grow weirdly that way. It's pretty cool how hailstorms form. None of them are the same. It's like snowflakes. It's pretty interesting. And this was from this past year. It was in February. This is not snow. This is hail. We had one little convective storm go over Endicott, and it produced small pea-sized hail, and so that was pretty interesting for a winter hail event. Now, lightning, again, not needed for severe thunderstorms, but you need lightning to call it a thunderstorm, because that's what creates the thunder. So you're going to get, within the thunderstorm updrafts, you're going to get charge separations. So once the updrafts get strong enough, they create big water drops or hail. They start smashing into each other, and the charges separate. So the hailstone will lose a negative or gain a positive, and they separate within the cloud. So up towards the top near the anvil, you'll start getting a lot of positive charges, and then you'll start getting a lot of negative charges towards the bottom. The ground is mostly positive charge. You'll get what's called leaders from the ground, as this positive charge will start kind of creeping up, and you'll get leaders from the cloud, where you'll get these negative charges creeping down, and when they touch, the lightning flows positive and negative, so you actually get the lightning flows from the ground up. Now you can get it the other way, where you can have some negative charges on the ground as well that might touch with a cloud in the sky with positive, but most of the time you're getting lightning from the ground to the cloud. And then you'll get inter-cloud lightning, so between clouds, and then intra-cloud lightning, which is in between the storm itself. And so that's kind of how lightning works, just a quick and dirty thing on it. And flooding. It'll be caused by slow-moving thunderstorms or training of thunderstorms over the area. I don't know if you were aware when we had some flooding up north over in Oneida County from the thunderstorms that we had moved through last weekend. That was pretty much, it's a flood-prone area to begin with, but we had 3 separate areas of storms move over through the day, and usually all it takes is 2, but when you have 3, it tends to flood up there a lot. And we had lots of water in basements and rivers and small streams overflowing roads, and some bridges almost getting completely covered. So and then other things that can cause flooding that isn't related to thunderstorms would be ice jams, which you got to have ice on the river, and we didn't have that at all this year, so that wasn't a worry. And then dam breaks, which are very rare. And then when you hear people talking about a 100-year flood or a 500-year flood, especially if you're dealing with flood insurance, it just means it has a 1 in 100 chance of occurring each year. So 1 out of every 100 years. So types of flooding: there's river flooding, which is ice jams, runoff from snow melt, excessive rainfall from tropical storms, training of thunderstorms over an area. This river flooding is usually very slow. It takes days to happen, and it's usually pretty well forecast ahead of time, and we can get the word out at least usually within a couple days before it happens to let people get ready for it. And then flash flood and urban are kind of the same. It happens from excessive rainfall over a short period of time, and usually occurs within hours of the event starting, 1 to 2 hours, depending on how heavy the rain is. And then it happens anywhere that there's heavy rainfall. And urban is pretty much the same thing, but because of the concrete and poor drainage in urban settings, it doesn't take as much rain to flood an urban area that it would like a normal rural field or farm or small town out in the countryside. I know Binghamton has a couple spots where it can rain. Doesn't have to rain that much and it'll start flooding. Streets will start getting flooded. Yep, yeah, exactly. So our area is actually one of the more flash flood prone areas in the whole country. And that is because of our terrain. Lots of hills, lots of mountains, lots of rivers, lots of streams. So we get a good thunderstorm or a good group of thunderstorms, and all that water has to rush down the hills into these smaller streams, flooding out towns and roads, and then eventually into the bigger streams. And if you get enough of that, then those big streams and rivers start to flood. I know we haven't had a real major river flood here since I believe it was 2017. The big one in 2011, yes, on the Susquehanna. So that was tropical storm related, and that's usually what it's going to take to get a big river floods to happen. It's going to take days of heavy rain from a tropical type system. Yes. Okay. So terrain plays a huge role. So we're going to take a little 5-minute break. Everybody get up, stretch your legs. If you have not signed in the back, if you signed in prior to the event, there's a list with your name on it. Just check so I know you're there. If not, just put your details on the blank sheet and we will get you in the database. But I will plan on starting again in about 5 minutes. forever. So now we're just going to talk about the severe weather products that our office issues and the Weather Service issues as a whole. So what we have is 3 categories. We have outlooks, watches, and warnings. So outlooks are for convective severe weather issued by the Storm Prediction Center in Norman, Oklahoma. And they are possible severe weather event in the future, anywhere from 1 to 8 days. It's a general threat. Sometimes they'll list why they think it's going to be severe weather, what ingredients are available for severe weather to happen, but it's not going to get into specifics. Now, a watch is when conditions are favorable for a weather event, and this will be issued by the office here in Binghamton, as well as the SPC and neighboring offices. We all collaborate together to kind of pare down where we want the watch to be, which counties do we want it to end at, the timing, all that stuff, because we want everybody to be on the same page. Lead time can be anywhere from a few hours, so the event could be in the afternoon and stuff has changed overnight to where it's gone from marginal to, yeah, we really need to let people know that something can happen in the afternoon, to, if it's looking real good, even a couple days out, 48 hours, we could issue a severe thunderstorm watch. And then a warning is conditions are imminent, severe weather is currently occurring, get to safety, and that is issued by each office on their own. So for outlook from SPC, this is the categories. So you'll have a general thunderstorm, which is pretty much just, yeah, there's going to be some thunderstorms. No severes expected. I mean, there could be some strong winds, but we're not really expecting much. And then one marginal, slight, enhanced, moderate, high. Our area gets put into slight quite often, and we will sometimes get into enhanced. It's very rare that we will get a moderate or high, just because of our location. So when you're in a slight, there's increased confidence is that some storms will contain damaging winds, severe hail, and potential tornado, and we're expected isolated to scattered severe storms. And then once you get up into the enhanced, we're expecting most of the storms to be severe. And this kind of how bad could the storms be? For slight, similar to storms you may experience a couple times a year. And then when you get up into the enhanced, it's like maybe once or twice a year, and then all the way up to the high where, it's a once in a lifetime type thing. So this would be the convective outlook that SPC issued on March 31st for that afternoon of March 31st. That afternoon from is valid from 13Z, so from 9 a.m. until 9 a.m. or 8 a.m. the following day. But pretty much this is for afternoon type event. So we had a moderate extending all the way along the Mississippi Valley and then enhanced out, and then we were in general thunder up here. We weren't expecting much. And this is what happened. So all these red dots are tornadoes. Several long track tornadoes. Like these aren't all like individual tornadoes. They went through and we had 177 tornado reports. That doesn't mean that there was 177 individual tornadoes. It was more than likely this is one tornado, this is one, or the same storm producing 1, 2, 3 tornadoes, something like that. But you can see the guys at SPC, they do a pretty good job of narrowing down where they really think the best shot for severe weather is. And this is preliminary, so that very well, these dots of wind outside very well could have been could have been storms or could have just been erroneous stuff. I'm not quite sure. But every other severe event happened within at least the marginal. A couple here in Erie County, Pennsylvania, were outside, but for the most part, they nailed it. So a lot of people have problems with watches and warnings. What does a watch mean? What does a warning mean? Aren't they the same? So there's kind of this one way of explaining it. So think of tacos. So you have a taco watch. So the taco watch, you've got all these ingredients ready to make a taco. You got the meat, you got the shells, the cheese, everything. You got it all in the fridge. You're ready to go to make a taco the next day. The next day comes, boom, I'm making tacos. So taco warning. You got tacos, you're eating tacos, tacos are there. Now, you can go from a taco watch but not get a taco warning. If you go to make tacos and all of a sudden your meat went bad, I don't have any meat anymore, so now there's not going to be a taco warning because I'm missing the most important ingredient in the taco, no meat. So just because a taco watch is issued doesn't mean that you're going to get warnings the next day. So you just have to think of a watch as all the ingredients are there and we're pretty confident that they're ripe for tacos the next day, but overnight the fridge might have broken, our stuff might have gone bad. So taco watch means be prepared. Taco warning means get ready to eat some tacos. So that's kind of, it's a different way of explaining it, because a lot of people have problems differentiating the two and think that if there is a watch, there's going to be a warning. It doesn't necessarily mean that. It just means be ready for it. So severe thunderstorm watch, this is kind of what it's going to look like if you go onto our Weather Service website, the SPC website. So this is all the counties that were issued in this one, this watch that was issued in June 1st of last year. So it would be valid from 2:15 in the afternoon until 10 for all these counties. And then you're going to get a text version, and the Weather Service issues watch in Central New York. Pennsylvania includes this, and then we're pretty much telling everybody be prepared for a chance for severe weather between these hours here. Then you get the warning. So you're within the watch, and now you got the warning going. So this is what it's going to look like. It's called a polygon. So we will draw it on the storm that we think is the severe storm and the direction that it is moving. And then we're going to give ourselves a buffer on the end in case it decides to turn left, maybe turn right. Or maybe this storm out here goes severe, and so at least if it moves into this area is covered, so these people here know that, which looks like it's actually Binghamton right there. Binghamton would be in a severe thunderstorm warning, so even though this cell might not make it there, this cell could. Or we could do one for kind of like for a squall line or a QLCS, we'll draw a bigger one that covers a much larger area, but this one itself was for this single storm right here moving in that direction. And you'll get a severe thunderstorm warning for parts of whatever county this is until the time, and then we'll talk about where the storm was, where it was moving, and then what the hazards are expected. 60 miles an hour, penny-sized hail. Source, radar indicated. If one of you guys called in and said, a quarter-sized hail just fell at my house, source would be spotter indicated instead of radar. So if we have spotter indicated in there, it's actually ground truth. We know what's happening. When it's radar, we're just saying radar showing it, could be happening, could not be happening. But when we start getting law enforcement, EM, spotter, that's when we know it's actually happening. And then impacts, what to expect from the storm. And then it'll give some examples of the cities, and then some precautionary tags at the bottom to show people what they need to be ready for. And then tornado warning. It's kind of the same idea. It's the same polygon drawn on the tornado and where we think it's going to go. And same thing, a hazard of a tornado, radar indicated. Like I said, again, if someone called in and said, I just had a tornado hit my house, that will be spotter. And we'll be able to say radar confirmed or spotter confirmed tornado instead of radar indicated rotation. And then we can update this based on what reports we get from people on the ground. So if they say, yeah, just knock down a whole bunch of trees, we can put that in the impacts, and we can say, a stronger tornado. We can change this text up here, manually edit it ourselves to indicate what's actually going on the ground based on the reports we've gotten. And then a flood warning. It's not as much of a time crunch as the severe warnings that we issue, because we want to get those out as fast as possible. A flood is a little bit more an event that takes a longer period to happen, but you'll get a box outlined of kind of where we think the flooding is going to occur or is already occurring, and then it'll be a flood warning. In this case, it was for rain and snow melt, because this was on Christmas of 2020. And so areas that it's impacting, and then kind of what we've seen so far, that 1/2 inch to 3 inches has occurred, while less of a quarter is expected to continue. Response is ongoing from the earlier heavy rain and significant snowmelt. This was after the 40 inches that we got from that snowstorm in 2020. And so you'll kind of see this box, and then the information will be in text form here on what to expect. So safety. Really want to hit safety based on some of the unfortunate incidents that have happened so far this year with people chasing tornadoes and reporting tornadoes. So with extreme wind, you do not want to be under trees. You do not want to be outside. You have to expect tree damage is going to happen in a severe thunderstorm. So you want to be away from windows, indoors, and the interior part of your house. You can prevent damage to your home by getting on top of it at the beginning, cutting trees away from your house, seeing any dead trees and cutting those down, making sure parts of your property are have tree limbs removed, so if it looks like it might fall on something, it's not going to. And so you need to know where to go. So this is specifically for a tornado, but if you have a strong microburster, strong straight line winds coming through, you definitely do not want to be in the attic or even on the second story. You want to be in your lowest part of your house at the most center room. So if you don't have a basement, you only have one single floor house like a ranch style, get into a bathroom with no windows in the middle part of your house. If you have a cellar, go to your cellar in the center part of the cellar. Don't be near a wall. Don't be near a window. Don't be near anything mechanical. Try and get to the, I mean, if your boiler and all that stuff is in the middle, then that's just where it is. But you want to get into the center part of your lowest level. So if you're caught outside, so you're outside driving your car and severe thunderstorm is coming, you get an alert on your phone that a tornado is happening, what do you want to do? Do not, under any circumstance, go underneath a bridge. It is the worst spot. It acts like a funnel, and it will amplify the winds from either straight line or tornado 2 to 3 times stronger because it just acts like a funnel. So do not go underneath an overpass. Do not go on an overpass. Find the nearest sturdy building and get inside. If you can't, if you're like out in the country and there's nothing around, get out of your car. You might think, oh, I'm in my car, it's a safe spot. It's not, because it can get tossed by the tornado. Get to the lowest point that you can find on the ground and lay as flat as you can and cover your head. So if you see a ditch, get into a ditch and lay in the ditch and cover your head, because most times people are going to get killed by debris versus getting killed by the winds from the tornado. So you want to get flat in some sort of ravine, a ditch, some depression in the ground to try and help yourself stay away from the debris from the tornado and or straight line winds. In a hailstorm, if you're at home, like I said before, it can be like a plink, 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 plink. So if you see that, run inside, get into the interior part of your house, away from the windows, and then assess the damage after it moves through. In your car, stay in your vehicle, turn yourself away from the windows as much as you can, cover your face. If you've got passengers in the back seat, have them pretty much look at each other and just hug themselves with their backs to the windows, because hail will do significant damage to cars. That's why the Midwest has hail sales all the time. Because the hail goes through a town and all the dealers have banged up cars that they'll sell for $10,000 less. And lightning. Lightning is a huge, huge problem. It kills and injures tons of people every year, especially in the summer. Everybody wants to be outside, golfing, boating, camping, doing all this fun outdoor stuff. But when you're outside, lightning can strike from up to 10 miles away. If you're in a field, you're the tallest part of that field. You are the lightning rod that when you're out there. Don't go under a tree, because the tree's the lightning rod. They can go right through the tree, pass to you through the ground. So you want to get inside. And if you are near a car is actually a great spot to get away from lightning. The lightning hits the car, and the frame of the car acts like yeah, there you go, thank you. And it pushes the electric charge away and keeps it on the outside. So you will be safe inside a car. And flood safety. Do not drive into floodwaters. Even if you think it's not that deep, it only takes If you're on your feet, it takes 6 inches. In a car, it only takes a foot to wash the car away. And then you're either stuck in a river and you're drowning, or you take hours for search and rescue to find you. So get to higher ground as quick as you can. Like I said, do not drive or walk into it, and be informed ahead of time. Understand what the weather is supposed to be like and be prepared for all possibilities that could happen. So what do you report and how to report it? So now we're getting into the nitty-gritty of the Skywarn Spotter program and what you guys need to do. So what do you report? We want to hear about tornadoes and funnel clouds. And when you're reporting that, anything about a rotation within a wall cloud, like, yeah, the wall cloud is spinning, that's great information. That you saw a funnel cloud, you see a tornado, and whenever you can, include pictures or photos. That helps us understand, helps us see it, and gives higher confidence to what you're reporting. Same thing with wind damage. What did it damage? Did the roof get ripped off, doors blown off, tree got uprooted or snapped? Don't call in and say a small branch fell down. That doesn't help. It doesn't help. I mean, we appreciate people calling in, but you're wasting your time if you're just going to call in and say a small branch fell over, because that doesn't help us at all. Anything with our warning decisions, if that could be a 20-mile-an-hour wind on a dead tree branch, we just don't know. And if utility wires and utility poles get knocked over, that's a good indication for us. And again, include photos. Hail, any size of hail is important. It's a good indicator of thunderstorm strength. So if you get pea-size hail or nickel-size hail, anything that even is sub-severe, we still want to hear about it. Measure it with a ruler. So you just pretty much put it in your hand, put a ruler next to it, take a picture. And then if you're calling on the phone, use a common object description like quarter, nickel, hen egg, I guess, if you know what a hen egg is. And then flooding. We want to know about flooding so we can issue flood warnings. Those are probably the most difficult thing for us to do, because we just don't have great tools to know where flooding is. We have some really good tools that have just come up within the last decade, but we still don't have the same, we just don't have the coverage of where it's flooding. So that's where we really need our spotters. Waters over road, stream rising that's near a full bank, especially when it's still raining heavy and it's still rising, or any flooding that's not common in your area. Like if you have a small ditch by your house that anytime it rains for a half hour, it always floods over the road. That's common. We're not going to issue anything based on that. But if you had another ditch where it never floods and it starts flooding, that's what we need to know. And again, include pictures. Pictures are our friend. We love pictures. So here's a good size. You can find this on the internet. Like I told a couple people, you will get this slide deck with the email that you signed up with. I will send this out either tomorrow or Sunday. So you'll get this entire slide deck. This size comparison chart you can also find on the internet, and it just kind of gives you an eyeball of what quarter, $50 for you older people, $50, and then golf ball, pool ball, baseball, and then another way to look at it as well. Estimating wind speeds. This is just kind of for your information. We don't really want you to call in and say, oh, well, I estimate a 55-mile-an-hour wind gust. That's a little bit out of your purview, but we would like to hear that, small tree blew over, or corn stalks got blown over, or widespread damage, stuff like that, or even some minor stuff. Even sub-severe winds are good to know about, so we can know if that storm needs to be warned as severe, or if we can not have to continue warning it as severe and maybe issue what's called a special weather statement, which is for storms that have sub-severe winds or hail that aren't going to be as damaging. But we still would like to know, if a storm goes over your house, what happened. What not to report. Do not call in and say it just rained a ton and it's really windy. That's not very helpful. Scud clouds look ominous. They are not anything that has to do with anything severe. So people will call in and say, it looks like a funnel, but it really isn't moving much. Scud clouds are low-level clouds that, as the air is rising, it hits what's called the lifted condensation level, where air will start to condense into clouds. Some parts will be lower than others, and so you'll get what looks like these fingers that are coming up because this warm air is rising, and it turns into clouds, and it's just kind of going up. It's just a scud cloud. It has no severe impacts at all. And lightning and thunder, you don't need to call in and tell us that you had a lightning strike. That's not important. And vague reports without measurements or damage, kind of like that there. So how to submit your report. This is the perfect information that we need and that for you guys to call when you're going to either call or write it in. Your source, your location, what you're reporting, and what time. So an example, hello, this is Jake, one of your spotters. I'm in Locke, New York, and I'm calling to report several trees down just east of town along Route 90 after strong wind gusts moved through about 15 minutes ago. So that gives me who I am, so I know that this is one of my spotters. The location, east of town, because Locke, New York, if you're just telling me you're in Locke and that several trees are down, well, Route 90 goes east and west through Locke, so which side is it? So where you're at, a direction within that town, what happened, several trees down, and along Route 90 after a strong gust, where it was, after what type of event, and the time. It doesn't have to be precise. We can use the radar to go back and see when it went through when we put our storm report out. But if you give us an idea, then we know kind of where to zero in on. So, review of reporting methods. How do you get a hold of us? So there's several different ways. This spotter hotline is for you only. Nobody else has this number. Do not give this number to anybody else. This is our spotter line reserved for spotters only. And we want this line to be open and not used for the general public calling to ask me what the temperature is like at their hometown a week from now. This is an important line we want to keep free. We want for you guys only, so keep it to yourselves and use it for reporting severe weather. You can email us at bgm.stormreport@noaa.gov. We have somebody that checks all this stuff during severe weather events. One of their jobs is to look for reports. So looking at that, you can also send a report online at this website that you'll have access to when I send it to it, but it's just a weather service reporting through the website interface. Facebook, Twitter, Instagram, this is usually where we get our most information, especially on Facebook. People in our county area love Facebook. Not so much Twitter and not even Instagram at all, but Facebook is huge. So we're always on Facebook, always interacting with the public there, and that's where we get most of our reports. Amateur radio, we have at least one licensed ham operator in our office, but it's not as active as it used to be. But we do get reports from radio clubs, especially for snow. They'll send us a lot of snow reports. But if you happen to be an amateur radio operator, we do have, during severe events, we do have our radios turned on, and we do have somebody that will answer them if you call them in. And then MPing, which you can get in the App Store, it's just a mobile reporting from this same type of thing, but it just works as an app on your phone. So how else can you get involved if you want to do something a little extra? You just don't want to be a spotter. You're really into weather. You really love doing this type of stuff. You can be a part of what is called our COCARAS program, Community Collaborative Rain, Hail, and Snow Network. So it's a grassroots network of volunteers from all ages working together to measure precipitation. So you pretty much, every day, you send in a weather report for snowfall amounts or for rainfall amounts. And it helps us understand if there's drought in the area, how much snow is on the ground, whether we need to be worried about a coming up rainfall. If we've had a lot of rain already, is it prone to flood? COCARAS is huge, and it gives us a lot more coverage than just the current automated stations that we have, because they're very sparse. And all it is this: you go online to Amazon, you buy a little, and the website COCARAS has a guide on what to get, but you just get this little rain gauge, and you enter a report on the computer, and it sends it in to us, and your report pops up on the map here. It takes like, 30 seconds, but it's another way to get involved if you want to do more than just be a spotter. So what's next? You all are now trained spotters for the Weather Service. Awesome. I have a certificate in here that I will put on the back that y'all can pick up to leave if you want one. You don't have to have one. It doesn't mean anything. I just designed it, so our old one was pretty bad. And I will send you an email with a copy of the certificate and a copy of the slides. We don't have spotter IDs. Some of our older spotters will call in with spotter ID, blah, 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 blah. That means nothing to us. We don't use it anymore. It doesn't, I still am gonna have to ask, okay, where are you from? All this stuff, because before you just use an ID, you typed it in and that gave you a specific location. We don't do that anymore. So to remain in our spotter database, you need to take this course again within about 3 years. We do have a winter course for snowfall. It's not as exciting because there's not tornadoes and stuff to talk about, and but it's pretty cool if you want to learn more about snow and how snow forms and sleet and freezing rain and all that stuff. It's very complicated, much more complicated than severe weather. And if you will really want to know more about severe weather, we have an advanced spotters course available. It's on the same website that if you went on to sign up for this, it's on our main website as well. There's a virtual version that I believe is in June, and then there is another in-person version I think is in Cortland, but I'm not quite sure off the top of my head. And that advanced will go deep. I reworked it with one of my colleagues, and it's a lot of radar stuff, and it's a lot of more in-depth severe weather formation stuff. So it's if you're a real weather nerd and you want to learn a lot more, that's what you want, because it gets real nitty-gritty into the radar, and radar is very, very cool, very complicated. So thank you. Here's my email address if you want to get a hold of me and have any questions. Here's our social media tags. It's pretty much all NWS Binghamton. I appreciate you all coming here, and I will take any questions if anybody has any.
All right. I was going to say, any questions here in the room? All right. Let me just check the live stream. Any questions on the live stream at all? We have a couple.
Cool.
All right. Let's see here. What do we have? By the way, we had one person watching us from Adelaide, Australia.
Hey, there we go.
All right. Where is it? All right. Question from Randy. Do you feel there's been a shift from the central U.S. to the southeast for spring tornadoes?
Yeah, I was just reading something about that, where over the last decade, the southeast has really had a lot more tornadoes than in their previous climate record. Don't know why. Don't know if it has anything to do with climate change or La Nina, El Nino. We're kind of really starting to get a better understanding on how La Nina and El Nino impact our overall weather patterns. It could have something to do with that, but I'm not an expert on the teleconnections, that type of stuff. But yeah, it's definitely, it's been an observed trend to, especially in the early spring for the southeast, to experience more severe weather. And it's a lot more what we call high precipitation supercells, so where it's a lot of rain, a lot of moisture coming off the Gulf, and those are the worst. I mean, I feel real bad for the people in the southeast, because it's trees everywhere. You can't see it coming. It's high precipitation, so the cloud tops are super low, so there's just no visual warnings. You got to have super awareness of what's going on that day. You can't just if you're in Kansas or Nebraska and you look outside, you can see storms coming from 50, 60 miles away. It just doesn't happen there. So they really have to be prepared, and there's a lot of underserved communities and a lot of trailer parks and stuff that just don't have the construction or the preparedness to handle it, and they are impacted the highest. And it's just, hopefully we can get some of these things sorted out within the next decade or so. But it definitely is a shift, and it's not great.
All right. Another question from the chat. Sort of, what if you live in a trailer? It seems like.
Yeah, if you live in a trailer, get in a car and drive away. You will not. If a tornado is coming, you need to get out of the trailer.
When you hear the alert, you need to go.
You need to go. You need to see where it's at and assess it. And if you can get to your car and bolt, because the trailer is not going to be tied down to the concrete more than likely correctly. It's not built the same way as a normal house is. It doesn't have the studs and all that stuff. So even an EF1, EF2 can really destroy it, and you're just not going to have the protection that you would in a normal house. So if you are in a trailer, understand that you might, what is happening that day, and if you're in a threat for severe weather, be ready, and be ready to get in a car and just drive away from it, because that'll be your best bet, is just to try and get away from it.
All right, got a question here.
I've got a loud enough voice. If you're in a trailer and you can't get out of it, what's the safest place of a trailer?
If you can't get out, you want to get, like I said before, you want to get into the center part of your trailer, away from windows if possible. If you've got blankets or pillows, try and put them on top of you and hold on to them, because it will somewhat help blunt some of the impacts from stuff that's blowing around. If you've got a tub, crawl inside the tub maybe to help do that. But it's just like a normal house. You want to be in the interior, away from windows, and covered up as much as possible.
All right, well, Jake, I want to thank you again for a great presentation, and I hope...
Thank you.
Nice that you sort of increased your spotter network here in the area.
Yeah, it's a great turnout.
And,
super excited.
For those that have a scanner possibility, I know there's at least four ham radio operators right here right now that we do in fact bring up a Skywarn network on a local ham radio repeater. So even if you aren't licensed, you can at least listen to it. And just even like a police scanner that even with those little ball fang radios, you can pick that up. So if you're interested in that, we can tell you about that.
What repeater would that be?
Okay, so for those that want to know, it's 146.865 megahertz is the one big local repeater. Normally what we do here at Kopernik, and I apologize, I was at another event that ran much longer than it was supposed to, and so I was unable to greet you earlier this evening. But we have a rule here that you can't leave Kopernik until you look through the telescope. However, tonight's not going to be the night. So if you paid to get in, we'll go back out to the cash register, and we'll give you a card to come back on another night for it cover your entrance fee. And again, for those of you who's here for the first time, just by matter of interest. Okay, a fair number of you. I'll give you a card too. People that come up here, they say, like, where did all these stars come from? You got to get away from the city lights to really pick it up. And so we'd love to have you come back on a night where you can in fact look through the scopes. And next Friday night we have another program. Actually, this one has to do with radio. How many know that there's actually a Marconi tower here in the area? Okay, just 2 people, 3 people, and 2 of them were hams. So if you remember, Marconi was the gentleman that invented communication through radio. Well, there was actually in Binghamton, Marconi did an experiment where he put some towers up right near the baseball stadium. There was also a similar set of towers down in Scranton, and he tested out the capability of communicating to a traveling train, a moving train between Binghamton and Scranton. That radio tower still exists here, and so next week we have a speaker talking about the history of that tower, and also if you're interested, on the next day on Saturday is International Marconi Day, and the local ham radio club will actually be down at that tower. We'll hang our antennas off of the tower just like Marconi did, and we will communicate with people around the world, and so you're welcome to also come down and see that. So one of the other thing also, if I know there are some youth in here, Kopernik has a really strong summer camp program. I know we've had I see some I was going to say graduates, some alumni, if you will, that we still have some openings. So if your child or grandchild has an interest in STEM, definitely check out on our website what we have to offer. And Anyway, thank you again for coming tonight, and we'll look forward to seeing you up here again soon. All right, good night.